Assalamu alaikum warahmatullahi wabarakatuh. This is the second part of this module, and in this part we're going to discuss these two points. We start with signal classification and properties, and then move to the basic elementary signals. Signal classification and properties, it is covered in the textbook in this section. And before starting talking about the signals in depth, somebody has to understand the difference between the dependent variables and the independent variables. I left these two links for you to go through. But just in brief, if we set an experiment and we want to measure, for instance, the voltage, so by default, we assume that there is an independent variable, which is the time, which we are using in this set of experiment as independent variable. So what we are trying to do is to monitor the voltage across time, how the voltage is changing based on how time is going on. So the voltage, is it increasing or is it decreasing or is it stable across time? So this is what is meant by independent variable. So we are trying to monitor across certain values. Now it is time, which is the vertical axis, and we are trying to plot the voltage, which is the vertical axis across that independent value. Now, when we talk about signals classification, there are different perspectives that we can go through, like continuous and discrete time signals, analog or digital, periodic, aperiodic, even, odd, deterministic and random variables, energy and power. And this last one will be discussed not in this video, in another video, a separate video at the end of this module. Starting with the first aspect of categorizing, of classification of signals, continuous time versus discrete time. Now we are talking about the vertical axis, whether it is time or space or any other different type of independent variables. So this classification determines by whether or not the time axis is discrete, meaning countable or uncountable. And the main difference between the two, that between each point on time, if it is continuous, we must find any point in between that has a value for the function. But if we pick two consecutive points at the discrete, the function in between these two are undefined. So this is undefined. It is defined only at certain points with a step size between them. So this is what we are talking about, discrete. So continuous time signals will contain value for all real numbers, and discrete, which will be only at certain sampling signals, certain sampling points. So those values are defined only at these certain values. Moving to the analog versus digital signals. For the analog signals, it is those which has the amplitude can take on any value of continuous range. Now we're talking about the vertical axis. So it could be taking the value here, there, any point. It could take any value in between. Compared to the discrete or digital signals, the vertical axis is taking only certain values, either here or there. It could be 2 values, 3 values, or whatever values, but it is digital signal. So the amplitude, which is the vertical axis, that we are talking about here. So in digital signals, it takes only certain numbers. A common example of digital signals is the binary sequence, which takes only 0 or 1. So it cannot have 0.5 for this cis-digital system. Compared to the analog, if this is 1 and this is 0, it could take the 0.5 in between. If we put all these four together and trying to analyze, see what are the possible outcomes it can come with. Now, if we're talking about the vertical axis and looking at the top side of these graphs, we can find both of them are continuous time. So at any point of time, you can find and define the function value. So you can define it here, you can define it here, you can define it in between. There is no problem. So this is continuous time. And this is again continuous time. If we look at the bottom side, the vertical axis, the t-axis, here and there, it is discrete. So these are discrete time axis, discrete time axis. So it can take only at certain points. If you come in between, this is undefined, and this is the same. It can take only at certain points. If you come in between, this is undefined. So this is for talking about the four plots from continuous and discrete perspective. Now, if we move to the digital and analog, we have to divide them on left side, as we can see here. For this signal, the y-axis can take any value of this function. So even in between, it could take this value. There is no problem. So also at this plot here, it could take any value between certain range on y vertical axis, and even if we try to check one of them in the middle, it is valid. We can define some functions that get this value. So at the left side, both are analog, so we call it analog. Signal, and we call this analog signal. If you compare it with this one on the right side, we will find that these two vertical axis cannot take numbers unless it is on a certain value. So only here or here. You cannot take any numbers in between. So that is called digital, and that is called digital value. So again, this can take either this side or that side. So therefore, if we want to conclude, we will find out that the plot number A is analog and continuous. So the plot number A is analog and continuous. The plot number B is digital and continuous time, and plot C is analog and discrete time, and D is digital and discrete time. Moving to a new perspective of these properties and classification of signals, we talk about the periodic versus aperiodic signals. So a signal is called a periodic signal if there is a period after which the signal is repeating itself. And in math, we can define it in this equation. So if we add to the t m, which is an integer, times a period t naught, it will give the same value of x of t. So as if we try to omit this part. And this is defined from minus infinity to infinity. And the smallest value of t naught is called the fundamental period. And if we want to get an example, so sine wave, everybody knows that the sine wave repeats itself in a certain frequency. So this is the first period, and it will repeat itself once this period is finished. So this one is repeating again here and repeating again here. So this is the fundamental period that we want to talk about. What about the following plot? So what about this one? Does this repeat? Yes. So if we look at this point compared to this point, it is exactly the same. And then it will be just zeros, and this is again the same zeros, and this will come up in this shape, and this will come up in this shape, and then this will continue all the way to the bottom, and this will continue all the way to the bottom. So in fact, this is the period at which it repeats itself, and this is the periodic signal. What about this one? So I mean, it might not be clearly from here shown it is periodic, so it is aperiodic signal, aperiodic signal. So whenever we have a, meaning it is not periodic. If this is having a period, so we call it periodic signal. So this is a periodic signal, and this is a periodic signal, so it is not periodic signal. If we want to discuss this concept in discrete signals, so the periodic signals is defined as this expression shown here, and normally we replace the time variable with n variable because it is integers, and then we will have this fundamental period as shown here. If we remove this, we will come back to the original value. So it is a signal which repeats itself. So if we remove the period addition here, multiple periods, then we will return back to the same value of the function. An example of discrete signal is a cosine function, and if we apply this, so we will take the n and we will replace it n plus n naught, and once we did this, we will have n is replaced by n plus n naught, and we open these parentheses and we come up with this value, which if this value is an integer multiple of 2 pi, which is the period of a cosine, then it will be an integer. So not each and every cosine function in discrete is periodic, so it has to have a condition, and the condition is given by this one. If it is a periodic, then we must find a value that satisfy this function, and this will be our fundamental period, and it has to be an integer. So I will leave these exercises for you to solve, and we will discuss it later. And this is another examples. Just take care about cosine here it is addition of cosine. So if this signal is repeating with a certain frequency and this is repeating with a certain frequency or certain period, so we will have a t a, for instance, and we have t b. So we have to find a way then if this is repeating every let's say 1 second, and this is repeating every 3 seconds, then we will add this together and see how it goes. Sometimes it will go with the bigger, sometimes it will go with the least common multiplication factors between them. And this is again another example of cosine times cosine. So it is cosine square. I will leave it for you to think about it and come with some solutions for discussion. If we move to the discrete signals, and you have to go with that conditions and try to find if n naught as an integer is exist or not. Does n naught exist or not? Moving to even versus odd signals. So even signals is any signals such as x of t is equal x of minus t. This is in discrete in continuous, and this is in discrete. So x of n is equal x of minus n. If we want to visualize this in plots, so even signals is normally in, if we're talking about 1D signals, we can visualize it as symmetric around the vertical axis. So if we have a mirror to flip whatever comes at this side and it is matching with this side, then this is an even function, and this is perfectly clear here and also there. So these two are even functions. Regarding the odd functions, it is the x of t is equal to minus x of minus t. Please take note that there is an addition of minus sign at this even odd signals, and it is exactly the same here for the discrete signals. And if we want to get some examples of odd signals, normally it is symmetry with respect to the origin. It's not a vertical axis anymore, it is respect to the origin. So you have to flip it 2 times. So whatever comes at this side, flip it to this side, and then whatever comes in the top, whatever comes at this side top and this side bottom, just replace them with each other. So 1 time, then second time here. So 1, then second time here. And this is clear here. You can see if you mirror it here, and then you mirror it from here across here. So you flip it first on vertical axis and second on horizontal axis, or vice versa. You can do the opposite. You can do first on horizontal axis, then in the vertical axis. You can flip it this side, then again this side. It will come to the same results. One of these other characteristics that we can characterize the systems, the signals, is whether it is deterministic or it is a random signals. So the deterministic signals are signals that can be modeled as completely specified functions. We can move from a certain plot into an expression with x of t is equal, like for instance in this case, sine of omega t. So we could model this plot into a certain behavior of a well-known functions. Compared to the random signals, in this case, the signal is moving in such a way it would be really hard to put these signals into a very well-known deterministic function. So it will be really difficult to put this one in a sine wave or whatever, but it will be somehow difficult to deal with as a deterministic. That's why we will work with it as a random signals, and these random signals will be not in this scope, the scope of this course. It will be somehow out of the scope of this course. But just I want you to figure out whenever you see random signals, then you don't need to do something about it, but just to identify that this is a random signal which is moving in a behavior or behaving in such a way that you cannot put it in a certain well-known functions. Okay, now coming back to our example where signals are just assumed to be a student who's entering a system which is the school. So let's see these properties or classifications of signals among these students. So if we're talking about continuous or discrete students, we can visualize a student from different aspects. Like we can just measure or get the readings of his vital signs of life, like blood pressure, body temperature, heart rate, respiratory rate, the breathing, this rate. So all of these we can visualize it as continuous or discrete signals. And a second one is a periodic or aperiodic signals. We can visualize like his screen time or social timing. So like if we focus on this or visualize it or plot it among daily perspective or among monthly perspective or just in an hour, and we watch these behaviors, some of them will be a periodic behaviors like his if we're talking about vital signs in the previous, like his heart beats, it will be periodic compared to these screen times, which sometimes it will be more aperiodic signals than periodic signal. Another aspect of the student could be classified as an even or odd, like his GPA or learning curves. If you try to see over his lifespan, sometimes at the college it will reach a peak, then it will go down. So if we plot this against the an x-axis, this will be an even function, and sometimes you will find some other type of things if you monitor the performance of students, or if you just try to focus on aspects of the student's life, you can find something which is even or odd functions. Deterministic or random, most of these are randoms, but sometimes you could find something deterministics. But let's give more examples of random signals like human voices or pictures. If you try to put it in a signal manner, it will be more of random than deterministic. Now I will give you a little bit more plots to visualize this. So if we're talking about the body temperature, so if you look at it from on one day, on one single day, and you monitor it continuously, then you would be able to plot it as you can see as a continuous time signal. And if you plot it among like days, like for 1 month, from day one all the way to complete 30 days or 31 days, then you plot the body temperature, then it will be more of discrete signals. And if you compare this with periodic or aperiodic signals, looking at his ECG or the heartbeat, it's more of periodic, repeating itself in a certain pattern. So this is more of periodic signals compared to the screen time that he spent. If he looks at his iPhone, for instance, you will find that most of these things are aperiodic. Maybe you could find some pattern followed in this one if you look for maybe creativity, which is assigned with classes. sometimes attendance, or reading some references if he is preparing for the exams. If you look from monthly wise or weekly wise or daily wise, maybe you could find some patterns and find the periodic signals. Otherwise, it will be aperiodic signals. And again, the social timing, if you are monitoring how much time he's socializing in a person, or he's invited in a parties or some larger group of this will be like a curve or a signal that you could monitor the students. All these different ways of interpreting the students will be at his entry to the college time. If you monitor it and then record it somewhere, and then after the college, he finished his college and he's at the graduate uh, time, if you have another snapshot of these things, then you would be able to figure out what is the impact of the system, of this system of the school, on these signals. So this is some sort of understanding what is like a practical example of our daily life on signals and systems. The last two properties that I was talking about, the even odd. So if you look at the learning curve or the GPA, he's trying to like the ability to get problem solved correctly. So this is an X person, Ian. So in week one of instructions, he was able to solve like one or two problems. Then it start improving on the time. So this is a signal. So if you put this one into the system at the first year and then compare it at the last year after he finished the college, maybe these things could change, and then we will know the impact of or the effect of the system on these students or signals if we want to understand it. And this is another way of how much time he's able, how much words he correctly he was trying to type per minute, like a typing skills. Another way of taking this is deterministic versus random. So random is just if you get a sample of human voice signal, will be clearly it is random signals. And also, if you get a picture of a person, then this is the x-axis, y-axis, and this is the x-axis, and try to plot the signal among the maybe the brightness or whatever. Then you could be able to figure out that it is not deterministic; it is random signal. Okay, moving to the second part of this lecture, which is basic element signals. Basic elementary or elements in the signals works as a building blocks to some bigger signals and bigger things. So we're going to see a small signals like these toys, and then using these toys we will try to build like a bigger house, like the kids who's working with games and blocks. In this part, we're going to first discuss the sinusoidal signals, then go to the sinc function, then exponential, then some basic signals basic signals of impulse, step, ramp function, which is used very frequently in the signals and systems. Then a little bit more like bigger type of signals constructed from these small ones. Then I will give just a generic form of signals and systems. Okay, now I will start with the continuous time signal, and then I will give the discrete version of it. So starting with sinusoidal signals, this is the expression of sinusoidal signals, whether it is sine or cosine, both works the same, with a phase shift between them of 2 pi. So if we consider this cosine function, then here is the expression and here is the plot. And I just want to make sure that you know that there are three ways to express or to present a signal. So these three ways of presenting a signal would be, the first one is numbers in tables. So these numbers. Then second one would be plots in figures. Third one will be expressions in functions. So these are the three ways how we express the signals, how we present a signal. So in this section, I want you to come familiar with the way, an expert to master the way how you move back and forth between these two uh, way of representations. So if I give you the plot, or if you saw the plot somewhere, you could easily find the expression from it, or if you get the expression, then you could easily go back to the plots. I'll give you an example here. So this is the amplitude. So you will figure out that the amplitude would be nothing but just this number here and this minus a over here from sinusoid. Then this is the frequency. So the frequency, you should be able to figure out that this, which is the period of the signal between the two peaks or between the two points at the bottom or between the zero crossing, would be equal to T naught, which is related to this frequency written here in this relation, 2 pi over omega naught. And then this would be the phase shift, and it would be expressed somehow with the difference between these two points. So this is, I would write the absolute value of uh, theta. So again, to the general expression of cosine function, if we neglect the phase shift, we can draw the cosine as you can see here with no phase shift. The phase shift is equal to 0. And then, as you know, the A is the amplitude, then the omega would be the angular frequency, and it is in radian per second. Sometimes it is, people would work with it in degrees. And here we can find the frequency of signal out of the angular frequency and the T naught as we discussed before. Now, if we introduce an omega, I just want to make sure that you understand that there will be a shift. So the entire signal has been shifted to the right. When we introduce a negative phase shift, it will be shifting to the right. We will come to this more in the signal transformation, but just I want you to figure out there is a difference between this and this plot, and what is the difference is just we add this minus omega or minus theta at this side. Now, what about if we want to look at the discrete time version of cosine or sinusoid? So in the discrete time domain, we will have the amplitude, as you can see here, which is somehow related to these values, and then we will have the angular frequency. And just I want to make sure that you understand that in discrete time, it is not necessary each and every cosine or sine is periodic. No, some of them are aperiodic. They're not periodic. So it is not repeating itself on a certain period. There is a condition to have a cosine in a periodic manner, and the condition is that if we could find an integer n that satisfied this equation. So this is an integer and this is an integer. So if you could find an integer n, then would be a periodic. Otherwise, this will not be periodic. So this is the fundamental period and this is the fundamental frequency. So when we talk about fundamental period, it will be between this point and this point. And if we want to find what is the fundamental period here, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the fundamental period here is 12. N is equal to 12. Another point which differs the discrete time from continuous time sinusoids, that you could find an identical signals with distinct value of omega. Let's see here. This is a signal A1 and signal 2, x1 and x2. So this is a signal 1 and signal 2. So each of these signals has different omega. So this is omega 1 and omega 2. If we were able to find or to choose these omegas in such a way that omega 2 is equal to omega 1 plus an integer multiplied by 2 pi, then these would be again an identical signals. So in this we can find that these omegas are separated by 2 pi's, then or multiple of 2 pi's, then they are identicals. And whereas compared to the continuous time signals, distinct value of omega always, it will never happen this way, always will give distinct signals, so it cannot have the same frequency. Okay, now we finished the sinusoidal, sine and cosine from time domain, continuous time, and discrete time. Now I just want to move to the sinc function. So the sinc function is defined as follows. As you can see here, it is sine by theta over by theta. So sometimes it's written this way: sine x times by over by times x. So somehow it is sine x over x. It is of two parts. The first part is sine, second part is 1 over x. So these two functions are multiplied by each other. So as you can see from the plot, at the beginning it will be reaching to 1, and then it will be decaying as 1 over x is decaying with the same rate of 1 over x. And it will be the same from positive side as well as from negative side decaying. So we can write it as x of t in equals to sinc of t. And if you noticed, the crossing of the horizontal axis will be at all these integers 1, 2, 3, 4 from positive side, and minus 1, minus 2, minus 3, minus 4 from negative side, and so on until you reach plus or minus infinity. What about discrete time? I will leave this to you and try to think about how many times you want to sample these signals and to see how these are changing based on the sampling rate of that you have chosen. You can refer back to the book with some certain there are some certain examples for you over there. Now, moving from sinusoidals and sinc function to the complex exponential signals. So the complex exponential signals are generally written in this format. So x of t is equal to c times a of t. So generally c and a is complex numbers. Let's talk now about a in particular. So a will be equal to capital A plus JB. So there are few cases. The first case, if it is purely real, then b would be equal to 0. If it is imaginary, purely imaginary, then a will be equal to 0. So therefore, for purely real, a will be equal to capital A, and for purely imaginary, a will be equal to JB. So here will be no imaginary part. In real part, there will be no imaginary part, and here there will be no real part. It will be just equal to this. Now, let's take it one by one. Now, if it is purely real exponential, so C and A all are real numbers. Okay, so now if both are real, let's consider now if A is greater than 0, then x of t will be growing. As you can see here, these functions are growing. And when A is equal to 1 here, e exponential of t, and this is exponentially growing. And this is an example of chemical reactions. And if A is less than 0, x of t will be decaying. As you can see here, it is decaying. And we take the example of e of minus t when A is equal minus 1. Here, A is equal 1. And this is very common in RC circuits. Decaying, the capacitor will be charging or discharging phenomenon. And then if A is equal to 0, then xt will be constant, meaning that xt will be equal to c times e0 of t. This will be equal to 1, so x of t will be simply equal to a constant c. So like 3, 4, whatever constant number. Okay, now moving to like a discrete case of x of n. So x of n would be equal to similar c times e to power beta n. And let's consider that e to power beta would be equal to alpha. So when we raise both to the power n, this side raised to power n, and this side raised to power n, then e of beta times n will be equal to alpha to the power n. As you can see here, this expression was replaced by this expression. Now, in discrete time, we have to consider a little bit more cases of alpha. So what about if alpha is positive? So now we are in the real number, and we are considering this is the 0 point, and this is, let's say this is 1, and this is minus 1. So when we say that alpha is positive, then we're talking about this region, and we are not considering this region. So if alpha was greater than 1, meaning this part, so when we talk about this part, this is case A, then we will find it is growing. So x of t will be growing. What about if alpha is positive, but it is in this side, where alpha is less than 1? So this is case B, and it will be decaying. As you can see here in the plot, this function would be decaying. Now, these are the two cases. Still, we have another two cases which we will see in the next slide. So in case of negative, let's draw this real-time, like real-time x-axis. So this is 0 point, and this is minus 1, and we're talking now about left side. So in case C, if alpha is greater than 1, so meaning this side, so absolute value of alpha greater than 1, meaning more less than minus 1, then it will be growing. But just notice it is alternating, one up and one down, one up and one down, and so on. But it is growing. And in the last case, case number D, if alpha is greater than, is less, absolute value of alpha is less than 1, meaning this side, so this is the last case D, and it will be decaying again, alternating. So these are the 4 different cases that I want you to visualize. Now, if we consider, we talk about A is equal to A plus JB, so we consider that it is purely real. So we consider that it is purely real in the first case. Now let's consider it is purely imaginary, so there is no real, it's just imaginary, so there is no A. In this scenario, we will write it A is equal J omega, not just B, we will write it J omega. And as you can see here, we just neglect the C. Let's see what is going on in this. Always it will be periodic. So these signals, always it will be periodic. And the period is T. And what is T? The omega naught would be equal to 2 pi over T naught. So this is the T. And why it is always periodic? And the reason why, if you separate these two into 2 parts, this will be equal to 1. And why is it that way? So let's consider that omega naught is multiplied by T here. So the T multiplied by T, it will be going away. So the entire thing here will become as J times this is taken off, this is taken off, and what is left is 2 pi. 2 pi. And if we want to move from polar representation to Cartesian representation, we would know that the magnitude here is equal to 1, and the angle is 360 or 2 pi, which is here. So it is nothing but this point over here. So this will be equal in Cartesian format, be equal simply to 1. So once any value times 1, it will be equal to 1. So this will go away, and like x of t will be equal to x of t plus t omega, which is the definition of periodic signals. Now just consider that both omega, j omega naught t and and exponential of minus j omega t has the same fundamental period, and this is proved using Euler formula, as you can see it here, cosine plus j sine. Okay, I will leave you to think about the discrete time and just review the book for the same sections in chapter 1. Now, this becomes a little bit complicated when we want to consider a complex exponential without considering a purely real or purely imaginary. So both sides are available over there. So this would be changed into 2 parts, or would be into 2 parts. The first one is a C, and the second part here we will put it as shown here. So using simplifications, we come up with this long expressions, and if we tried to plot the magnitude of that, we will find out that if r is positive, the one that we're talking about here, if r is positive, then it will be oscillating and it is growing, and if r is negative, then it will be oscillating but decaying. I think this is just worth knowing it, but not to take something about it seriously in the exams, but just maybe just a rough idea about this consideration. Again, the discrete time, maybe somebody wants to have a look on them on the book. Now, we have finished these basic well-known functions, sine, cosine, sinc, and exponential, and we are moving to these basic functions which is used heavily in signals and systems. The first one is the unit impulse function. In continuous time, the unit impulse function is defined as it is equal to 0 everywhere except at the point 0 itself. It will go to infinity. So meaning that it will be equal to 0 everywhere, here, here, and there. All is equal to 0, and once it reaches the point 0, it will go very sharply to infinity. To simplify the understanding of this, we need to look at the integral. So the integral of, by definition, the integral of this unit impulse function is equal to 1. And how this is achieved, if you look at a simplification or approximation of this function, let's consider a rectangular function which has a width of epsilon and a height of 1 over epsilon. As epsilon approach 0, this height will approach infinity. So 1 over epsilon will approach infinity. So as the width here becoming narrower, narrower, smaller, smaller, almost 0, small width here, this height will shoot up till it reach infinity. And if somebody wants to calculate the area under this rectangular, he will just multiply the width by the height. So this will be equal to epsilon times 1 over epsilon, which is equal to 1. And this is what is the definition of this integration. So an integration is the area under the curve, and it will be equal to 1 once this reach 0, infinity, and this reach the width reach 0. So in discrete time, it is much easier to explain than if you talk about continuous time. So the t-axis will be n-axis, and at the point 0, it will be equal to 1. That's it. And elsewhere, it will be equal to 0. So it is very simple compared to all other examples. So it will be 0 everywhere, and except at the point 0, it will be equal to 1. Now, the second basic continuous time signals is the step function. And if we're considering unit step function, then it will be equal to 1 if it is positive, and if it is at the positive t, then it will be equal to 0 at negative t. So in negative side, it will be equal to 0, and once it reaches 0, it will go, and at the positive side, it will become 1 to infinity. What is the relation between the step function and the impulse is that if you want to integrate the impulse function, you will get the step function, and if you want to derive the step function, you will get the impulse function. Again, if you want to talk about discrete time, you will be looking at an axis, and at the 0, it will become 1. Before the 0, it will become zeros, and after the zeros, it will keep itself to the same value of 1 all the way to infinity. The third one is the ramp function, and we're talking about unit ramp function, so you just multiply it by t. So just simply, if you multiply u of t times t, which is the step function times t, you will get this. So it will be equal to t, which is a linear function of t. And after you reach the negative side, you don't continue the same. No, you have to move to 0 axis. So that's the definition of ramp function. And again, the relation between the unit step function, to integrate the unit step function, you get the ramp function. And if you take the derivative of ramp function, you will get a step function. Okay. Now we will move from these basic functions to a little bit more complicated functions, which is constitutes of the combination of more than one functions from the previous three functions. And the first one is the rectangular function. And the rectangular function is defined as equal to 1 between minus half and half. So between minus half and half, it will be equal to 1. So this is the function equals to 1 at this region. Otherwise, or otherwhere, it will be equal to 0. So otherwise, everywhere else, it will be equal to 0. So I just um, So now I just want you to think about a way how to construct this function, rect function, from u of t. We could think about different ways how to construct it from u of t. And one of them is just considering that if we do have this u of t, okay, now this is the 0 point, then I will just shift to the left by half. So this is the first step. So this is step number 1. I will shift it to the left. Then I will have another signal and shift it to the right. So this is signal number 2. This is 1. And this is signal number 2. It will be shifted to the right by 1/2. Now what I need to do is to do 1 minus 2 subtraction between these two signals. So once I did this, 0 minus 0 will be equal to 0, and then at this moment it will go up because 1 minus 0 will be equal to 1 until we reach here. 1 minus 1 will be equal again to 0. So this will be 1, and this will be equal minus half, and this is half, and which is the function that we're looking for. Now think about discrete time. If you want to represent the discrete time, the t-axis will be n-axis, and then you will have a couple of functions, couple of things here, and then it will go to 0 again. And you need to make sure that this is wide enough to have more than one sample in your function. What about the next step is the triangular function, which is called tri, and it is given by this function, which is 1 minus 2 times absolute value of t, and this expression will give this plot. So it will be absolute value of t between minus half and half, and which is given as a triangle. That is the name. That's the reason why the name was given as a triangle function. And maybe you can think about a way how to construct the signal from the other basic signals. I would recommend you to think about ramp function. Now we're moving to have the generic definition of functions. So this is the generic signal definition. I just want you to consider that this is the real number. So take segments of this real number. Let's say it is 5 segments. So this is segment number 1, segment number 2, segment number 3, segment number 4, segment number 5. So we have like -1 and 0, then 0 to 1, and then 1 to 2/3. So let's write these numbers here: -1 to 0, and then 0 to 1, and from 1 to 2/3. So in this region and that region, it is comes up under this otherwise. So 1 and 5. So this is will be equal to 0. Then at the second region between -1 and 1, it will be equal to -1 here. So simply just this will be equal to 0, and this will be equal to -1. Then if you consider the second period, which is from 0 to 1, it will be equal to t squared. So then t squared will be just simply somehow this way. Then after 1, the function is defined as equal to 1, and this will be equal to 1. It will be connected all the way to till here. Then it will go to 0 because number 5 will be equal to the same. So this is how we plot this function, and in this representation, x is defined above different pulses over different period of time. So there's certain definitions of each period of time. So we put in segments, periods of time, and then we define this function accordingly. By this, we conclude this lecture. Thank you for listening, and see you next time. Assalamu alaikum.